This talk will be on what we do in the area of secure hardware, or actually cryptographic hardware design, and it will be focused on efficiency and agility. And when I was thinking about giving this talk, I thought that actually efficiency and agility are also good goals to strive for in life. So that's why at the end of this talk, I will try to draw some analogies with like priorities and things that dominate or occupy our lives. When we talk about secure hardware, what do we mean? Like why, what, how? We all know that when we look at electronic systems that store, communicate, process personal data or company critical data, that security is important. And so we need to make sure that these electronic devices are secure, and to make sure that they are secure, that doesn't come for free. So there's always an additional cost due to security in power or energy consumption, in performance overhead, or in cost. So for example, actually that's in the next slide. So we always need to take into account like these parameters or requirements when we develop a secure system. And which parameters are important depends on the application. So, for example, when we look at pacemakers, then low energy is important because we want the battery to last as long as possible. When we look at RFID access control systems, then low power is important because the RFID tag needs to be powered wirelessly by the reader. So we need low peak power consumption. When we look at video conferencing system, then high performance, or actually low latency is important. And when we look at disposable medical sensors, then low cost is important because these sensors do not last long. We want to be able to throw them away. For some applications, it's enough to have a general purpose processor to meet these requirements. But for other applications, it's not enough to have a general purpose microprocessor with some software code running on it. So for those applications, we need specialized hardware to do the cryptographic or algorithms, or to run the cryptographic algorithms. And the overview that I put here shows the whole spectrum. Actually, on the left side, you can see fixed chips, or ASICs, and on the right side, you can see general purpose microprocessors. And as you can see, ASICs perform better when we look at speed or performance. They also consume the lowest power or energy. And when we look at high volumes, or when high volumes of these chips are produced, then they come at a very low cost. And general purpose microprocessors are completely on the other side. And then we have some different types of platforms in between. So the research that we do concentrates on this part. So we look at fixed chips, ASICs, but also at configurable chips, field programmable gate arrays, or FPGAs. So this is the focus of our research. And more specifically, in this presentation, I will concentrate on two important goals in cryptographic hardware design. And first one is, like the title already said, efficiency. Where, like, what do I mean with efficiency? Depends on the application. For one application, efficiency means high performance. For the other application, it means low energy, low power. And for the other application, low cost. And we have to achieve this while having a very high security level. The other goal is agility. In security research, or in security in general, we never know what's coming. There might be tomorrow a new vulnerability detected, and that means that all systems need to be updated. So we need to make sure that electronic devices are also agile. So not alone, it's not enough to make them very efficient, but we also need to make sure that we can apply updates or upgrades when necessary. And I will first look at this first goal, so efficiency. So what do we mean with efficiency? I already told you, like low power, low energy, high performance, low cost, etc. When we look at hardware technology, how do we try to achieve, or how do researchers try to achieve high efficiency? First of all, traditional technology research focuses on shrinking chips, making transistors smaller, keeping up with Moore's law, which says that the number of transistors in a chip doubles every 2 years. But it's not easy to keep up with Moore's law and to keep on shrinking, actually, due to physical challenges. I will not go any deeper, but also due to economical challenges. Like, for example, Global Foundries announced last year or a few years ago that they would not go into 7-nanometer technology because the cost of the infrastructure is just too expensive. So that means that it's not easy to keep on shrinking and shrinking. And that's why emerging technologies, as we call them, pop up. And with emerging technologies, I mean everything that's not standard silicon chips, but something alternative. And they are proposed to improve efficiency. What we are currently concentrating on in this field is on 3 emerging technologies. The first one is focusing on very, very low-cost systems, so ultra-low-cost systems, using digital circuits on flexible plastic substrates, so actually plastic chips, let's say. Second topic is on low-power, low-energy circuits using I will not go into detail, but fully depleted silicon on insulator technologies that are specifically designed to go to low power and low energy applications. And then third one, ultra high performance, using the newest FPGA platforms to do network intrusion detection, so network security applications. And in this presentation, so the research question here is actually, how do cryptographic circuits behave in these emerging technologies? Like in silicon chips, we know more or less how, what kind of side channel leakage to expect, how to protect against this, how these circuits will behave in general with respect to security. But in these newer technologies, we don't know. So the first question is, how do they behave with respect to like these efficiency parameters, but also with respect to security threats like side channel attacks or key hiding and things like that. I will just briefly say something only on the first topic, because there's not too much time, on the plastic circuits. So these plastic chips have been around for a while, and maybe you've seen some of these applications. So actually they are like in widespread commercial use for flexible displays. And in these flexible displays, the transistors in the chip are used to drive the pixels. But a bit over 5 years ago, researchers realized that these transistors can also be used to build digital circuits and to have really some functionality inside, not only just driving pixels or controlling pixels. And what people mainly started looking at were RFID or NFC applications that require very low power and that are not battery powered, but that need their power or to get their power wirelessly. And then some examples are like flexible labels, intelligent packages, smart blisters for pills, or electronic medical patches. Besides that, like circuits that have already been fabricated are NFC transponders, even small microprocessors. And that's why we wanted to look also into security or crypto applications, about which I will say something later. So what are the biggest differences between this plastic technology and the traditional silicon technology that we know? I will just go very quickly over this slide. As you can see here, many things are worse in the plastic technology, but the thing that's better is the cost. So in the one but last row, you can see that these chips are much cheaper than traditional silicon chips. And they are also bendable and stretchable because they are made on a plastic substrate. Another difference is that there is no dedicated memory technology like flash memory for non-volatile storage, so we need to find other things, and those other things are very low-tech, like just cutting wires to program bits or use ink to connect wires. That's it. So that's what we have, and now if we want to build secure systems out of that, what are the challenges? First challenge is that it's still not possible to have a lot of functionality in these chips because of reliability issues. And we saw that the smallest crypto circuits that we wanted to build already had more transistors than the largest circuits that were proven to be working up to now. That's the first challenge. And then second challenge, these chips are not packaged. They are bare dies. If you look at a normal chip, then it's in a package and you cannot see what's inside. But in this case, it has to be bendable. There is no package. So you can just see everything that's there. So if we then want to program the key using these low-tech methods like cutting wires or using ink drops to connect wires, then we can just read out the key. So that's the second challenge. Then I'll just briefly say how we addressed these challenges. Yep. So we chose a very, very, very small crypto algorithm, the Katantan algorithm that showed to have the least number of transistors. We also made a very, very small serial design, and we managed to put it on this technology and have a working chip with a working test setup, so everything was tested. So the first challenge we managed to overcome by choosing the right algorithm and by designing a very small hardware architecture. First challenge, tick. Second challenge, prevent the key bits from being read out. This is a microscope image of our chip, and on the top you can see how the key bits are connected. If we zoom into 2 of these key bits, then you can easily see where wires have been cut and where they have not been cut. So you can just easily see what the key bits are, actually. We proposed a way to mitigate this by not cutting wires, but by putting transistors on the spot where these wires are, and then by using a laser to change the mode of these transistors, actually by adding extra doping to these transistors such that they change their state, just to say it a bit bluntly. And this is then what happens, but I will not go into details because that would lead us too far. And the result was that these are microscope images of transistors that we lasered, and you should not be able to see visually a difference between 2 of them, but still they are in a different state, so you cannot distinguish between one that's conducting and one that's not conducting, which corresponds then to a wire and a wire that has been cut, without somebody being able to see that under a microscope. So actually our security challenge that we tackled to begin with has been solved, let's say. So the results were that this was published, and we intend to go on with this. Then, second goal of our research is to have agile circuits. Like I said, if some vulnerability pops up, we want to be able to deal with it and change the circuits or the implementation. So why, what, how? Cryptographic agility is what we want to achieve, and cryptographic agility is the ability of cryptographic hardware or software to be updated when a new vulnerability arises or when new standards are imposed. Why do we want this? We saw in the past that there were many algorithms used in very important applications in our daily lives that did not survive and that were broken. So we want to put them aside, and then there have been many initiatives also, like new standards proposed to solve these things, and also ongoing competitions to find new algorithms to solve this. Also in physical cryptanalysis, like side channel attacks, fault attacks, we saw a lot of evolution, and I will just click. I just listed a few things, but this is what it looked like in the past years, like all kinds of new vulnerabilities and defenses that popped up. And this is actually the motivation, together with theoretical cryptanalysis, why we need cryptographic agility, why we need systems to be updatable and to make sure that we can adapt the systems in order to thwart these or to mitigate these vulnerabilities. So how can we achieve crypto agility? If we look back at this overview, then we can add another dimension, and that's programmability. So a system that's programmable, we can update, of course, and upgrade. Productivity is also important because a designer or an engineer needs to be able to come up with new implementations to put on the system. So what we actually want is a system that has maximum performance, minimum power energy consumption, minimal cost, but maximal programmability and productivity. So how can we achieve that? FPGAs are a good solution, but the question is, are there better solutions? And then if we look at what has been done in previous work, then most solutions come up with some kind of coarse-grained configurable architecture for which you need to use new design tools that then the inventors developed for their special configurable platform. We don't want to do that. We want to be lazy, and we want to reuse the experience of electronic design automation companies because they have been around for 30, 40 years, and it doesn't make sense to make our own tools. So that's the first thing. We want to maximize productivity. We don't want designers to learn new languages to be able to program these new configurable hardware architectures. So we want to use existing things like VHDL, high-level synthesis tools, etc. And of course, we want to optimize efficiency. So how do we do this? If you look at a normal FPGA, it looks like this, a regular structure with some lookup tables, a design flow on the left. Like I said, we want to reuse part of this design flow because it's based on decades of experience of big companies. And that's why we keep the FPGA structure, but we try to find replacements for these small lookup tables that are inside. And we do this, or we did this, by looking at what would be the most efficient to implement crypto algorithms. So we want to replace these general purpose lookup tables that are there in FPGAs by other building blocks that lead to more efficient, adaptable, or agile crypto implementations. And then, to cut a long story short, we did some exploration and evaluation. We came up with this. We evaluated it by implementing many ciphers, and we found out that we could have a huge area decrease with similar performance and also huge decrease in configuration memory that's needed. Target application platforms would be upcoming eFPGA platforms. These are embedded FPGAs embedded into an ASIC, into a chip, to have part of the chip being reconfigurable. This is already used a lot for communication, to be able to change or adapt to changing communication standards. In this case, we can also add our eFPGA blocks for cryptography, such that we can still update the crypto on the chip after deployment. And another possible application could be in FPGAs, because FPGAs already have many dedicated building blocks optimized for digital signal processing, for memory, for high speed, etc. So why not add a configurable crypto building block that can then be more efficient than implementing the crypto on the existing lookup tables in the FPGA. So we also published these first results, but we're looking a bit more further into this. So to summarize, 2 important goals were addressed in this presentation in cryptographic hardware. And as I promised in the beginning, I saw some analogies with life, so in secure hardware, but also in life. So how can we address, actually, efficiency and agility are also very important in life, because everybody has priorities or things that you want to do in life, and it's always hard to combine, and you only have a limited amount of time, so you need to be efficient to be able to do what you like, to be happy. You need to be agile because life changes. You have many phases in life. Things can change very suddenly, so you need to be able to adapt. So I thought about it a bit, and so I listed what's important to me in life. So in alphabetical order, family. I only have 2 kids, not 4 kids, so these are the same kids on the top pictures. It's just that there they are younger and there they are older. My son also has a better hairdresser now, just like Ahmad, who especially did his hair for this event. Yeah. Then friends are very important. Some friends are here, so that's very nice. Sleep is very important. Sports. You can see some pictures. Actually, Leila is on the picture on the left there. Time for myself and work. These are, maybe I forgot something, but for me, these are my, the most important things in my life. So how to find a balance between all of these things, and the balance is also continuously moving. First thing is setting priorities. For us, we decided to get external help for some things, like cleaning and sometimes taking care of the kids. Choices also need to be made like in combination with partner's job, so there's always a trade-off, let's say. But very important is also to let go of perfectionism. I think it's impossible to be like a perfect mom, perfect wife, what did I write? In perfect shape, with perfectly clean house, perfectly raised kids, and an outstanding career. Impossible. So you can only do your best. And I mean, if you do your best and you're happy with yourself, then that should be more than enough. Yeah, keeping a good energy level is important, I think. So sports and sleep are important. And also to be efficient, good combinations are important. Like, I like to combine sports with friends, combine sports with family. When I travel for work, I see this as time for myself, which I enjoy also. So I'm not bothered by like missing the kids or something. I just try to enjoy. I try to sleep well when I'm traveling also. Luckily, work and friends can also be combined, and there are many examples here today, so it's nice to have trust relationships also in work. And bad combination is work and kids, so it should be separated because it doesn't work. And then I would like to conclude with this slide. It's actually not my quote, but it's from, I don't know, Brian Dyson, former CEO of Coca-Cola, and he said that like life is like juggling balls, 5 balls. Most of the balls are glass balls, only the work ball is a rubber ball, which actually means that you should put things into perspective. Like if the health ball drops, it's glass, you might not be able to restore it. Same goes for family, friends. Yeah, spirit, actually, no, it was in the picture. But put things into perspective. If something goes wrong in work, you will be able to fix it, or, I mean, find something else, and just take care of all those other things as well, and do not get carried away. So that's it. I conclude there.
Thanks. So we have time for one question, maybe 1.5. Yes.
Thanks for your talk. I'm not into hardware, but I'm interested to know something. From a communication protocol perspective, we use this term of agile framework for protocols. With this design framework, a lot of downgrade attacks have been introduced, where the main attacker goal is to reduce the level of security, to force one or both party to convince the other that they cannot go to the higher level of security or algorithm. So I'm curious to know if this type of attack also applies to hardware agile design or not.
Yeah, so definitely. I mean, that's also something that would be applicable to this, but I think it resides at another level. So first we try to make it technologically possible to have agile hardware, and then at another level we have to make sure that the update happens in a secure way, that we don't get like downgrade attacks, like you say, just like for protocols, actually. So you are completely right that this is, that this could be a possible attack vector. But that's like the next step to look at that, and we can learn from protocol people there, I'm sure. Yeah. Thanks.
One more short question we can take. Oh, okay, Nele is still here, so ask her later. Let's thank the speaker again.